Now members, we are going to focus on a uniform or a rectangular distribution. This is an example of a cartesian distribution, and a random variable x is said to be a uniform distribution if x follows r into on that interval of a to b, if its probability density function is given by this. So the moment you see that the intervals here is what they subtracted, then they got their its fraction, then that's what we call a uniform distribution. Now what happens to the sketch? If you are sketching now, know that how we sketch these points, this is our f of x. So our PDF is defined by this. So we need its value at x equaling to a, and then its value at x equaling to b. But this one is just a constant function, meaning we don't have any x there, meaning at this point A it's going to be the same, and also at point B it's going to be the same as you see there. Then plot it so that our f of x is going to be on the vertical, and the point there right now is a constant there. So if you reline from A up to B, this is what we get. And there is generating something like a rectangle, and hence that's why the name a rectangular distribution comes from. And we want to see, is this a perfect PDF? Because something is called a PDF if the area under that PDF or that function is a 1. So instead we are getting the rectangle. So what will happen, we know that the area of a rectangle is given by length times a width. So our length from here, this is our length from here up to here, this is going to be, we are going to get b, then the length here we get b minus a. Then times our width from here up to here. So the length from here up to here is 1 over b minus a. And see, if I multiply this, I get b minus a over b minus a, which will be a 1. So since our area under this PDF is 1, then this one is a PDF. Hence, f of x equaling to 1 over b minus a is a PDF. Why? Because we've seen that its area under this, the area under this curve is 1. So from there we shall see something very important in the uniform distribution. That's what we call the mean. Some people call it the expectations. How do we get the expectation? Know that whereas our expectation is equaling to x times the PDF of that function respect to x. So now our x here is going to be, we are integrating now from this interval. So it's that our interval of that PDF is from there. So we are integrating from A to B, then x times our PDF, which is 1 over b minus a to the whole x. And now you said this one is a constant, so we pull it out. So from there our x is going to be 1 over b minus a integral x dx from a to b. If I integrate this, I'll be having 1 over b minus a into, this will give me x squared over 2 from a to b. And substituting these limits, this will be 1 over b minus a into, when we put in b, we have b squared minus over 2, then minus, when we put in the lower limit. Now it's that here we have the same LCM, so this would be 1 over b minus a into b squared minus a squared over 2. And we say, remember this is the difference of the squares. So this will be, when you take this b minus a into now, this is going to be b minus a multiplying b plus a, the whole over 2. Why? Because we see that we know we have b squared minus a squared, the same as b minus a, then b plus a, using a difference of two squares there. And now you see that the whole of this can cancel with this. So remaining with now b plus a all over a. Therefore, our expectation always of a rectangular distribution is b plus as A the whole over. Sorry, this is 2 not A. This is 2 the whole over 2. So this is going to be so important in the next lesson. We are going to see how do we use this in there. So that's how we prove. Some questions they will say it like prove that the expectation of a uniform distribution is this. You just go through the steps as simple as that. Now, the next question we are going to see how we get the variance of still a uniform distribution, and then we see examples there. See you there. Go call.